optimization purpose. Okay, so basically two types of designs are used. First one is nothing but the simultaneous optimization, and by means of that of your sequential optimization. Same designs are used for the screening purpose as well as for the optimization purpose. So what is my optimization? Whatever the inactive ingredient we use for the formulation purpose, same time we use the different excipients, that is nothing but the inactive ingredients. Polymers we use for that development of that formulation. So how much will be the concentration of that formulation? How much will be the concentration of that inactive ingredient? Excipient ka concentration will be how much? Okay, that will be by optimization process or the optimization techniques. Same time, which process is best for your formulation? You people have synthesized the different product in the medicinal chemistry or in the organic chemistry. So for synthesis of the same product, we are having the multiple processes. Is it right? Each and every process are having some of the advantages, some of the disadvantages. On that basis, we are selecting that method. Okay, so that is nothing but the screening, and optimization is nothing but the best method that are chosen for the product. Okay, so these are the some methods, that is nothing but the factorial design, fractional factorial design, again Plackett-Burman, central composite design, Box-Benkum design, mixture design, and the optimal design. Okay, so out of these all the methods, so today we will only discuss about the optimization methods. So that is nothing but the full factorial design, okay, and the fractional factorial design. So both these designs comes under the factorial design. Okay, third one, that is nothing but the Plackett-Burman design, that will be used for the screening purpose. If number of factors are more or the number of excipients used in that formulations are more, then it is critical thing or the critical, it is difficult to identify the critical parameter. If 10 number of critical parameters we identified, so which are having the most important out of that 10 that are screened by means of the screening factor, that is nothing but the Plackett-Burman design. Okay, so we will neglect that screening because this QBD is a wide concept. It will take much more time to discuss all these designs. So instead of discussing all these designs, so today we will only cover the two designs, that is nothing but the full factorial design and the fractional factorial design. Okay, we'll start from the factorial design. Factorial design was first introduced by the Fisher in 1946. So he is the scientist. He's first time discussed this factorial design. Okay, it involves the study of the effect of each factor at each level, thereby identifying the main effect as well as the interaction between the factors and the different level. So what it states that to study the effect of each factor at each level. Okay, for an example, each factor, each level. So before discussing this factor level, first we have to discuss about the terms that are used in the factorial design. That is nothing but the factor. So which is the factor, or we again term it as a variable. Factor is nothing but the, again two types of factors are there. First one is nothing but the independent factor or the independent variable, and second one is nothing but the dependent variable. Independent variable means the input, in simple words. Dependent variable is nothing but the output. What kind of inputs we have provided, on that basis only we will get the output. Which excipient we use, how much is the concentration of that excipient, which process we implemented for processing of that formulation, this all are comes under the input. And what will comes under the output? Quality of the formulation that we tested after development of that formulation or during the processing of that formulation. Okay, so the effect at each factor means, for an example, binder ka concentration is one of the factor, disintegrant ka concentration is one of the factor. Okay, again force that are applied during the compression of that of your tablet is one of the factor. Okay, so these all are the inputs. And what will be the output here? Hardness of the tablet. If we increase the force, ultimately hardness will be more or less, that will be more. Okay, same time binder ka concentration, if the concentration of binder will be more, what is the impact of that binder concentration over the hardness? Less hardness or more hardness? People has discussed that tablet, na? Yeah, okay. Okay, that hardness will be more or less? That will be more. Disintegrant ka concentration, if we increase the concentration of disintegrant, the effect of disintegrant concentration over the dt time will be more or less? If we increase the concentration of the disintegrant, ultimately within a short period of time that tablet formulation will be disintegrate. So same, the effect is nothing but the each factor means binder ka concentration at each level. If we consider the two levels, low level of that binder concentration and the high level of that binder concentration, means we are getting that two effects. If that binder concentration is at low level, how much is the hardness? If that same binder concentration are having the higher amount or the higher concentration, what kind of hardness we are getting? At low level of that binder concentration, at high level of that binder concentration, two effects we obtain. If you consider the three levels, low, medium and high, so we will get that three effect. When binder concentration is low, hardness is how much? When binder concentration is at the medium level, how much is the hardness? When binder concentration is at the high level, so how much is the hardness of that tablet? Okay, now the number of experiments in the full factorial design is designated as x raised to n. So how it is x raised to n? So this x raised to n is nothing but the, on that basis we will only get the number of batches that are obtained by considering the design, by considering the design of that experiment. So what is meant by x? X represent the number of levels and n represents the number of independent factor or the independent variable. In simple words, we say that this is the input. Which is our input? Our output is depend on the input only. You are getting my point? Our output is only depend upon that input. What input we have provided for that development of that formulation. Okay? X raised to n is equal to the, that is nothing but the, this is the formula we use for that of your full factorial design. So this is all about whatever the discussion we have discussed here, this is all about the full factorial design. Okay, x raised to n. So how much number of levels that formulator has selected raised to the number of factors. You are getting the point? If this n ka value is increases, if the n ka value is increases, same time that number of trials that are obtained by means of the full factorial design also increases. Okay, the selection of factor and their level is critical because as the number of factor and level increases, the number of experiment simultaneously increases and its mathematical interpretation also becomes difficult. If we increase the number of factors, same time the trials also increases. If we increase the number of levels, we are getting in-depth knowledge or that of your each interaction. Okay, but same time number of trials also increases, same time cost associated with the optimization also increases, time associated with that of your optimization also increases. Okay, now we'll see that. Okay, so this kind of representation we obtain for the three types of factorial design. in the first example, two factors are there. Okay, according to this formula, n stand for, yes, n stand for the factor. How many number of factors are there? X stand for the number of levels. Okay, so in the first example, number of factors are 2. Which are these two? This is the factor 1 and this is the factor 2. Okay, same time only two levels are considered, the low level and the high level, low level and the high level. Is it right? So number of factors are 2, means x is 2, same time n is also 2. Okay, so how many number of trials we obtain here? 2 multiplied by 2, it is 4. If we select the 2 level for the 2 factors, that formulator need to prepare only 4 batches for the optimization purpose. You are getting the point now? Okay, now second example. In this example, how many factors has been considered? x1, x2 and the x3. Is it right? Means n is how much? 3. Is it right? Same time, how many levels are considered here? -1, +1, -1, +1, -1, +1. Means the number of levels are 2 or 3? Number of levels are 2 or 3? Only 2. Okay. So according to our formula, it is 2 raised to 3. Means 2 multiplied by 2 multiplied by 2. 2 to 4, 4 to 8. So 8 number of batches we obtain in the 2 raised to 3 factorial design, when number of levels are 2 and number of factors are 3. Now third example. In this example, only 2 factors has been considered, x1 and the x2. Is it right? So ultimately n will be 2. So how much will be the level? -1, 0, +1. -1, 0, +1. So how many levels are there? 3. So the number of levels, according to the formula, 3 raised to 2 means so the number of trial batches we obtain, or the number of trials we obtain for the optimization, will be the 9. If we follow 2 raised to 2 factorial design, then 4 batches will be obtained. We need to prepare, or that formulator need to prepare the 4 batches. 2 raised to 3, 8 batches. 3 raised to 2, 9 batches. Okay. Now in this example, 2 raised to 2, 2 factors are there, x1, x2. 4 batches we will get. Is it right? So how that 4 batches will be obtained? So this is the 1, 2, 3, 4. Is it right? So this is the first batch. In this batch, the concentration of the first excipient, or the concentration of that first polymer is low. Same time, concentration of second polymer is also low. If we consider that formulating variable, again 2 types of variables are there, formulating variable and processing variable. Okay. If we change the concentration of excipient, this will comes under the formulating. Processing variable means if we alter the process compression speed at low compression speed, again at the higher force applied. So this will be the processing variable. Drying time, mixing time, so this will comes under the processing variable. Okay. So first batch containing the factor 1 ka concentration is low, factor 2 ka concentration will be also low. Second batch, concentration of the first factor is high, concentration of the second factor is low. Third one, concentration of the first variable is low, but the concentration of the second variable is high. Fourth batch will obtain the concentration of the first variable is high, as well as the concentration of the second variable, or the concentration of the second excipient, is also high. Okay. Now second, this is which type of design? Yes. This is the example of 2 raised to 3 or 3 raised to 2? 2 raised to 3 means total number of batches obtained from this design will be 8. How that 8? 1, 2, 3, 4, 5, 6, 7, 8. Okay. In the first batch, all are minus means all the 3 factors at low level. This is plus 1, minus 1, minus 1 means first factor at high level, remaining 2 are at the low level. This one minus 1, plus 1, plus 1. First factor at low level, remaining 2 are at high level. This one plus 1, plus 1, minus 1. Initial 2 are at high level and third one at the low level. Okay, so in that way we will get that of your we say that diagrammatic representation of or the graphical representation of that factorial design when we consider 2 raised to 2, 2 raised to 3 or 3 raised to 2 design. Okay, now we will take one of the example so that will comes under the full factorial design. Okay, so in this example that formulator has prepared the sustained release tablet of metformin. Okay, so metformin tablet is used for the treatment of diabetes mellitus, type 2 diabetes mellitus. Is it right? Okay, so that formulator has to prepare the sustained release metformin tablet means what he is expecting from that sustained release formulation. It will accelerate the drug release or it will sustain the drug release or it will delay the drug release. It will sustain the drug release. So this kind of expectation has been expected by that formulator from this formulation. Okay. So for preparation of this metformin sustained release tablet, that formulator has used the metformin as the active ingredient against the different excipient. So which are these excipient? Microcrystalline cellulose, that is nothing but the diluent, then ethyl cellulose, PVPK13, magnesium stearate and the aerosol. So how many total number of inactive ingredients are present? Yes. How many excipients are present or how many inactive ingredients are present in that formulation? First one is that the metformin is your API. Okay, same time how many excipients are there? First one MCC, ethyl cellulose, PVPK30, magnesium stearate and the aerosol. Is it right? So total 5 inactive ingredient present in that formulation. Okay, if we apply the full factorial design by considering all the inactive ingredient, in that case our design will be x raised to n means how many number of factors are there? How many number of factors are there? 5. And the number of levels if we consider the 2, only high and the low. So total number of batches will be 2 multiplied by 2 multiplied by 2 multiplied by 2. Again 2. 4, 8, 16, 32. If we consider the 2 level for the 5 factors, we will get the 32 batches if we apply the full factorial design, means each factor at each level. Is it right? Okay. Now, so we are having that 5 inactive ingredients. So we need to screen that factors. So it is first step, we need to screen that factor and reduce that number of independent variable. So ultimately within limited number of trials we will optimize that formulation. Okay. So after screening, that formulator has selected the 3 factors only. Which are these three factors? Microcrystalline cellulose, that is nothing but the diluents. Ethyl cellulose, that is nothing but the sustained release polymer. And last one is nothing but the PVPK30, that is nothing but the binder. Out of the 5 inactive ingredients, that formulator has selected only 3: diluent, binder and the sustained release polymer. Okay, were taken as the independent factor based on the preliminary risk assessment study or by means of the screening factors, and same time he had selected the dependent variable, that is nothing but the drug release profile, percentage of drug release obtained at particular time, that is nothing but the drug release profile. Okay, so what we conclude here? So 3 independent variables has been selected. Okay, first, second, third. And what is our dependent variable? What is our dependent variable? Fourth one is our dependent variable. Okay, then we are concluding these results of this dependent variable by considering the independent variable. Which is our input and which is our output here? Input is binder ka concentration, sustained release polymer ka concentration and the diluent ka concentration. So these are the inputs. 3 inputs we considered, we selected. And which is our output? We will study the drug release profile. How much amount of the drug is released at that particular time. So that is nothing but the drug release profile. Okay. Now, so these are the independent factors or the independent variables: x1, x2, x3. First, x1 is nothing but the microcrystalline cellulose, x2 is nothing but the ethyl cellulose, and the x3 is nothing but the PVPK30. Okay, now levels, we consider only 2 levels, low level and the high level. So ultimately, is it right? So we'll get that design, full factorial design will be the 3:2, means total number of batches we need to prepare by application of the full factorial design will be the 8, 3:2 factorial design. So the microcrystalline cellulose ka lower concentration is 80 and higher concentration is 100. Then ethyl cellulose 5 and 10. Then last one is nothing but the PVPK30, 3 is the low and 5 is the high concentration. Okay, so same way we will get that 8 batches. All the 3 are low, then first is high, remaining 2 are low, then first is low, remaining 2 are high, then first 2 are high and fourth one is low. Same way we will get that 8 batches. Okay. Okay. So now that formulator has prepared that 8 batches by considering the inputs or the design selected by that software. Okay. After preparation of that 8 batches, he checked the drug profile or the drug release at 12 hours. After 12 hours, how much percentage of the drug has been released. Okay. So in the first batch, he has got the 80% of the drug release. Second batch 78, 65, 64, 72, 71, 62 and the 60% of the drug release he has obtained after preparation of that 8 batches by considering the different combinations, and he checked the dissolution profile of the drug release at the 12 hour. Now, total how many batches we prepared here? Yes, 2:3 factorial design. How many batches we prepared? 8 batches we prepared. Okay. So from the 8 batches, 7 effects are obtained. How many? Total 8 batches we prepared. From that 8 batches, we are getting that 7 effect So how these 7 effects? So individual 3. So total 3 raised to 2 factorial design. Sorry. Eight batches we obtain. Okay. So from that 8 batches we are getting the 7 effect. How that 7 effect we obtain? So first 3 effects are the main effects. x1 का individual effect, x2 का individual effect, and this x3 का individual effect. So these are the 3 main effect. Okay, then 3 two-way interaction. 3 two-way interaction. So which are these 3 two-way interaction? x1, x2, x1, x3, x2, x3. So you are getting the point? 3, again 3 two-way interaction. So total these 3 plus these 3 total are 6. Now again third effect will be obtained, that is nothing but the x1, x2 and x3, and that is nothing but the 1 3-way interaction. Total 7 effects you obtain. So out of that 7 will be segregated into the 3 parts. So 3 main effects, x1, x2, x3, 3 two-way interaction, x1, x2, x1, x3, x2, x3, and 1 3-way interaction. In that 3-way interaction, x1, x2 and x3, all the 3 will play an important role. Okay, so see here, x1, x2, x3, x1, x2, x2, x3, x1, x3 and x1, x2, x3. So total how many batches we are getting here? Total 8 batches. Is it right? Okay. What that first batch state that? In the first batch, concentration of the first factor is low, concentration of that second factor is low, then factor 3 is also at the low level. Means all the 3 factors at the low level. Is it right? These are the 3 effect we obtain. Now combine effect. x1, x2. x1, x2 is plus. So why it is plus? Minus 1 multiplied by minus 1, it is plus 1. Done? Okay. Then x2, x3. Minus 1 multiplied by minus 1 plus 1. Same x1, x3. Minus 1 multiplied by minus 1, it is plus 1. Now third is x1, x2, x3 is minus 1. So here minus 1 multiplied by minus 1 multiplied by minus 1, minus minus will be plus, plus 1 multiplied by minus 1, it is minus 1. You are getting the point? So same will applicable for the second batch. Plus minus minus means first variable is at high level, remaining 2 are at the low level. So same output we obtain here. Then third, minus 1 plus 1 minus 1 means first and third variable is at the low level and the second one is at the high level. Again minus 1 plus 1, initial 2 are at the low level and third one at the high level. Okay, seventh one minus 1 plus 1 means first one is at the low level, second one and the third one at the high level. Then 8 1 plus 1 plus 1 plus 1 means all the 3 variable at the high level. You are getting the point? So by considering the interaction effect, at the end we are getting the optimized batch. Okay, so this is all about the full factorial design. Okay, under the factorial design we are getting that two designs, so full factorial design as well as the fractional factorial design. Okay, so I hope so we'll stop here only. Okay.